Good day everyone, I am Adriana Fernandez and welcome to my presentation about computing power unveiled, where CPU evolution, GPU overview, and SAP1 operations. So today I will discuss and we will explore how CPUs and GPUs process information, trace the evolution of computing, and dive into SAP1 operations to understand fundamental processor function. So let's get started. First, we have here the presentation outline where we have the list of the topics that we will tackle. For our first topic, how a CPU works. So, a CPU is known as the central processing unit, and it is the brain of a computer. And it is responsible for executing instructions from programs. It performs calculations, make decisions, and manage data flow within the system. For the components of the CPU, here are the main components of CPU. First is the control unit, and for its function, it directs the flow of data and manage the execution of instructions. For Arithmetic Logic Unit, or the ALU, it performs arithmetic such as addition, subtraction, and so on, and logic operations such as AND, OR, and NOT. For registers, so it is a small high-speed storage location that temporarily hold data. For example, it includes the accumulator, where it stores results of operations, and program counter that tracks the next instruction. We also have the cache memory, a small fast memory unit that stores frequently used instructions and data. And lastly, we have the clock. It determines the speed of operation by generating rules to synchronize tasks. For the cycle, we have the fetch, decode, and execute cycle. So the CPU operates using a repeating cycle. So as I said, it is the fetch, decode, and execute cycle. So for the fetch, the CPU fetches an instruction from memory, or the RAM, or random access memory, using the program counter, and which holds the address of the next instruction. So the instruction is loaded into the instruction register, or also known as the IR. For the decode process, the CPU's control unit ciphers what the instruction means. It determines if it involves arithmetic or data movement or logic operations. For the execute, the ALU performs calculation or logical operations, and the result is stored in registers or memory. And of course, the program counter updates to fetch the next instruction. So lastly, for how CPU works, I will also discuss CPU performance factors. First, we have the clock speed, where it determines how many instructions per second the CPU can process. Number of core, multi-core CPUs can execute multiple tasks in parallel. And cache size, more cache memory allows faster data access. And lastly, the instruction set architecture, or the ISA, where it defines the supported machine language instruction. So that's all for our first topic, how CPU works. Um, Next, we have the evolution of CPU, the mechanics of a CPU. So I have here the timeline for the history of CPU. For during the mid 1960s, the miniaturizations revolution began with the development of integrated circuits, allowing dozens of semiconductors based transistors to be packed into a single silicon chip. This laid the foundation for modern computing in 1971. So Intel introduced the 4004 CPU featuring 2300 transistors, that capable of executing up to 92,500 instructions per second. They about the video, they also mentioned that compared to ENIAC, which executed only 5,000 instructions per second, the 4004 represented a significant leap in processing power. And so over time, CPUs have evolved dramatically, as mentioned in our video, that with modern processors like the Intel Core i9 7980 XE, performing over 80 billion instruction per seconds. Next is the data representation. So for the data representation, computers use binary bits to represent data. A single bit can be either 0 or 1. As you can see in our picture, we have that 1 as up or on, or it is activated. If 0, down, off, or not activated. So we also have the words. So for words, or also known as the multiple bytes, a CPU's architecture determines its word size. So for example, the Intel 4004 operate on a 4-bit word, whereas modern CPUs typically use 64 bits words. So for signed and unsigned representation, a byte can be interpreted as values from -128 to 127. It is designed, or 0 to 255, and it codes as unsigned. For instruction set, we have the definition here. The instruction of it is a set of instructions a CPU understand is known as its instruction set. So each instruction is represented in binary or the machine code, and often has a human readable counterpart, so the assembly language. So for the instruction, typically fall into categories such as arithmetic. The For example is the addition, subtraction, and any arithmetic logic that we can encounter. So next is the logical operation, as I mentioned earlier, the and, or, and not, and data movement, the loading and storing data between memory and registers. And lastly, the control flow, the branching and looping. Again, for the fetch, decode, execute cycle that I mentioned earlier. So here I will also discuss it again because it is in the video. So for the fetch, decode, execute cycle, according to the video, CPUs operate by continuously cycling through these three stages. So first, fetch, the CPU retrieves an instruction from memory or RAM via the address bus. Then the program counter or the PC will keep tracks of the memory address of the next instruction to be fetched. And next, decode, the CPU interprets the instruction, where breaking into opcode operation and operand the data or memory location. And this process may involve microcode, which is a low-level sequence of instructions that's stored in the CPU that helps translate complex machine instructions into simpler hardware and level operations. And lastly, the execute stage. The CPU performs the instructed operation, possibly modifying data in registers or memory. So the Arithmetic Logic Unit, or the ALU, is then the responsible for performing arithmetic and logical operations. So we have here for the fetch stage, we have the um what we call the program counter. So as I mentioned, it keeps track of the memory address of the next instruction to be fetched. And for the decode, this process may involve microcode, as I mentioned, which is a low-level sequence of instruction stored in the CPU that helps translate complex machine instruction into simpler hardware-level operations. And for this is for execute, not decode. So the Arithmetic Logic Unit, or the ALU, is responsible for performing arithmetic and logical operations. For the function and definition of data bus and address bus, uh, first we have the data bus. It transfers actual data between the CPU and RAM. Its width determines how much data can be transferred simultaneously. For the address bus, it specifies memory locations. A wider address bus allows a CPU to address more memory locations. For example, a CPU with a 32-bit address bus can access 4.2 billion memory locations. And for the opcode and operand, for its function, we have the opcode. It specifies the operations such as the add, move, and load. And for the operand, it specifies the data memory or memory location the operation acts upon. So for example, an instruction might have an opcode for addition and an operand indicating the numbers to be added. Next, we also have the immediate values. The immediate values is the operands embedded within an instructions, and the memory addresses is the operands that reference memory locations. Uh, and for the clock, uh, it is also introduced in our evolution of CPU. So the CPU's performance is regulated by an internal clock. So it measured in hertz, and a higher clock speed results in more instruction executed per second. And modern CPUs have clock speed in the GHz range, and where it billions of cycles per second. And the clock synchronizes operation and ensures orderly execution of instruction. So this GHz is the gigahertz. So next, for the challenges of speed and heat, of course, it is also mentioned in our video. So speed bottlenecks. As CPU get faster, accessing memory or the random access memory becomes a limiting factor. So techniques like caching mitigate this. So heat generation, higher speed lead to increased power consumption and heat. So for these efficient cooling solutions such as heat sinks, liquid cooling, and thermal running are required to prevent overheating and damage. So that's all for the first evolution of CPU. So for our next topic, the evolution of CPU again, about the rise of the x87. So for our introduction, as the 1970s progressed, CPU designs advanced significantly with faster clock speeds, larger address capacities, and more elaborate instruction sets. So by 1972, Intel released the 8008, an 8-bit successor to its 4-bit product line. So this microprocessor marked a significant milestones in computing history, both for its technical advancement and its impact on the software industry. So for the Intel 8008 and its feature, it's have several key features including the 14-bit address capacity, where it's allowed for more extensive memory access than its procedures or the predecessors, and a larger instruction set providing more programming flexibility, and more registers enabling improved data manipulation, and lastly, indirect addressing, a mechanism that allowed memory locations to reference the memory locations, enabling more complex software techniques. For the indirect addressing and vector tables, so for description, indirect addressing allows a memory location to store a pointer to another memory location. This capability is useful in various applications such as selecting a random sentence from predefined list using a vector table. A vector table maps numbers to specific memory addresses, allowing efficient retrieval of data. So we have here the example. So if a program needs to randomly pick one of 5 stored sentences, it can generate random number from 1 to 5. Next, use this number to look up an address in a vector table, and lastly, retrieve and process the corresponding sentence. And the role of, we discussed the role of interrupts. So these interrupts allow hardware signals and CPU events to temporarily pause program execution to handle high priority tasks. So once the interrupt service routine is executed, the original program resumes. So for example, it is mentioned in the video, the mouse event handling. When a mouse moves, the hardware sends a signal to the CPU, pausing the current program to execute mouse-related code. So this code updates the cursor position and register any clicks before allowing the CPU to return to the main program. So interrupts are essential in modern computing for handling real-time events and multitasking. Next is the Intel 8080, a major milestone. So in 1974, Intel released the 8080, considered the first truly practical microprocessor, and its featured is this, our presentation, the 3.1 megahertz clock speed, a significant improvement over previous models. So as we recall earlier, we have the gigahertz and now we have the megahertz. The 16-bit addressing, allowing up to 64 kilobytes of memory. Lastly, the external bus controller, where it facilitating interaction with RAM and I/O device or the input-output devices. So for the birth of the 8 times 86 architecture, we have the Intel 8086. So again, on June 8, 1978, Intel launched the 8086, the first processor in the famous times 86 line. So for its key advancement, it's included the 16-bit architecture, where featuring 8 general-purpose registers. Next is the segmented memory model, allowing up to 1 MB of memory. And lastly, the stack mechanism, supporting efficient functions called and data handling. So as you can see, we have now the 1 MB of memory, not only 64 KB. So next is the understanding stack operations. So for the description, the stack is a memory instruction and used to store temporary data and return addresses during subroutine calls. It operates on the last in, first out, or the LIFO principle, similar to spring-loaded cafeteria tray dispenser. So for that, we have the example. So using a stack for subroutines, first a program calls a function pushing the return address on a track, and next the function executes and returns the result, and the return address is popped from the stack, resuming the main program. So I have note here, if stock management is incorrect, it can lead to stock overflow, potentially crashing the system by overwriting critical memory locations. For the CISC versus RIS architectures, here I have the comparison. So the 8086 cemented Intel's commitment to complex instruction set computing, or the CISC. Unlike reduced instruction set computing or the RISC processors, which prioritize simpler and faster instruction. So CISC CPUs provide more complex operation directly in hardware. So for instruction complexity, uh, CISC is complex and varied, while RISC is simple and uniform. For execution of the speed, CISC can handle multiple cycles per instruction, while RISC only can handle one instruction per cycle. For code efficiency, uh, CISC can handle more compact but may be slower, but in RISC requires uh, more instructions. And lastly, for hardware complexity, CISC is more complex and RISC is simpler. So that's all for the part 2 of the evolution of CPU. Now we can tackle about the evolution of CPU, the origin of modern operating system. So, for instruction again, or 1, 2, 3. So that's all for the evolution of CPU and for the part 2. And that's all for the part 2 of our CPU evolution. So next is the evolution of multitasking in CPU design. So the evolution of CPU, the origin of arithmetic. 1, 2, 3, go. So that's all for the part 2 of our CPU, or the evolution of CPU. 1, 2, 3. So that's all for the part 2 of the evolution of CPU. Next is the, again, evolution of CPU, but the origin of modern operating systems. For our introduction, during the 1980s, the evolution of CPU design saw groundbreaking innovation that laid the foundation for modern computing. One of the most significant advancements was the introduction of multitasking, a capability that allows multiple processes to run concurrently on a single CPU only. This transformation bridged the gap between early computing and the sophisticated interconnected systems we use today. Next, so the early forms of multitasking. Again, for the recap, in the 1960s and 1970s, the concept of multitasking gained traction primarily in mainframe computing world. So the earliest implementation, known as the multiprogramming, allowed programs to be processed in batches. So the CPU would switch between programs during hardware wait times and optimizing usage. So next, so we have here a more advanced form or time sharing emerged, enabling real-time processor switching. So IBM's system 360 and operating system like DESYS, PDP-6, IBM OS, 360 MFP, and Multics, especially Multics, played a crucial roles in refining multitasking. Now let's dive into the influence of Unix. So, as I've mentioned earlier, multics play crucial roles in refining multitasking. So, multics heavily influenced the development of Unix, which became one of the most powerful multitasking operating systems. So, Unix principles can be seen in modern operating systems such as the Linux, Mac OS, and Windows. By the 1980s, multitasking was making its way from mainframes to personal computers, prompting CPU manufacturers to integrate multitasking support directly into their processors. So, what are the challenges of single process environment? So, in early single process, operating system had full control over CPU and memory, but suffered from uh, inefficiencies. And it includes first, waste CPU power when waiting for input. Second, we have the system process due to bugs or invalid operations. And lastly, the dependency on programs to return controls safely to the operating system. Uh, then, we have the multitasking strategies. Uh, this is two, cooperative multitasking and the preemptive multitasking. In cooperative multitasking, um, a process, so a process uh, voluntarily yielding control back to the operating system. If a process fails to return control, the system could become unresponsive. So, for example, Macintosh system software initially used cooperative multitasking but faced stability issue due to poorly designed applications. While in preemptive multitasking, um, it addressed this stability concern by enforcing time-sliced CPU access. The operating system actively managed processing switching, preventing one process from monopolizing the CPU. Modern operating system, including Windows, Linux, and macOS, where it employs preemptive multitasking for efficient resource utilizing. For memory management and protection, so multiple processes reside in memory simultaneously. To manage this efficiently, CPUs introduce memory management unit or the MMUs. So the MMUs enforces memory protection by restricting processes to their allocated memory, preventing crashes and security breaches. I have here the example for memory protection. So next we have the okay. These MMUs also introduce memory access privileging, preventing lower privilege programs from tampering with critical system resources. Next is the virtual memory and paging. So, virtual memory abstracts physical memory location, allowing programs to assume that they have access to a continuous memory block. So, the MMU maps virtual addresses to physical addresses, enabling seamless execution. For paging, memory is divided into fixed size pages, with the OS dynamically swaps between RAM and disk storage when needed. So these techniques enable system to run applications that exceed physical memory capacity. So here we have the example of the memory and swapping. We also have the impact of GUI-based multitasking. Of course, for the history, in 1980s saw major advancement in graphical user interfaces or the GUIs. Apple's Lisa in 1983 um, and Macintosh in 1984 pioneered GUI-based computing. So Through early Macintosh systems locked through multitasking later versions, introduced multi-finder, enabling concurrent program execution. So for other GUI-based systems, it includes the Amiga OS, the Advanced Preemptive Multitasking Capabilities, and the Atari ST, the run on the Motorola 68K CPU with GUI multitasking features. We have also the role of Macintosh 68K processor. So the Motorola 68K series was instrumental in advancing personal computing during the 1980s. So the key features we have here is the 32-bit internal architecture with 16-bit ALSUs, the 8 general purpose register and 8 address registers, and the flat memory addressing without segmentation. So I have here the note that while early versions lacked built-in multitasking support, the external MMUs enabled features like memory protection and virtual memory. So the rise of the Motorola 68K. For recap, the 1980s revolutionized computing with advancement in CPU design, enabling the shift from single tasking to multitasking. So, the Motorola 68K dominated embedded system and gaming, while the Intel 8286 introduced protected memory mode, paving the way for modern OS multitasking. So, um, over the decade, production cost of the Motorola 68K processor declined, making it an ideal choice for embedded systems. So it became widely used in video game system into the early 1990s, network and telecom equipment, television, set-top boxes, laboratory and medical instruments, and handheld calculators. As you can see, we have here the pictures of those examples. Video game, the network and telecom equipment, the handheld calculators. Next is the IBM PC-80 and the Intel 8286. By the end of 1984, IBM launched the IBM PC-80 featuring the Intel 8286 or the 286 processor, a major leap forward for personal computing, and this processor introduced protected memory mode, a critical feature that allowed for more sophisticated multitasking and improved system security. And this picture is the example of a computer that has 8286 processor. Next, Microsoft Windows and cooperative multitasking. So, alongside hardware advancement and software development was also progressing. So Microsoft had been working on Windows since 1981 and it's in 1983 Windows 1.0. So it made its public debut and running atop MS-DOS Windows introduced a graphical user interface or the GUI and cooperative multitasking. So through initially considered a flop compared to Apple's GUI, Windows set the stage for modern GUI-based multitasking and established a long-standing relationship between Microsoft Windows and the Intel 86 architecture. So next, now we will tackle to the 8286, a game changer in CPU design. So in Intel's 8286 processor was groundbreaking in its ability to support multi-user systems with multitasking. So it's included an advancement memory management unit and supported several forms of virtual memory and memory protection. We have here that three key changes contributed to its improved performance. So we have here the list, the elimination of multiplexing, dedicated addressing unit, and the improved prefetching and pipelining. And I will discuss this in the next slide. So first, elimination of multiplexing. As you can see in the picture, we can allow more data to be processed per cycle. Next is dedicated address unit. So the 286 introduced a dedicated address unit to accelerate memory operation. And lastly, the improved prefetching and pipelining. So instruction unit could prefetch and decode up to 3 instructions at once by speeding up execution. Next is the protected memory mode and segmentation. So for this, memory addressing expansion, the 8086 processor could only address 1 MB of RAM due to its 20-bit address bus. And the 286 extend to its 16. From 1 MB, it extend to 16 MB of RAM using 24-bit address bus. Next is the segment memory model. Memory was divided into two segments that could be dynamically allocated. So each segments had an 8-byte descriptor that will manage by the MMU to define its location, size, and access permissions. And for the privilege level and security, uh, introduce a 4-level privilege system, it restricting access to memory and preventing unauthorized execution. And this is for the security. And for the implemented the global descriptor table or the GDT and local descriptive table, the LDT, to manage system-wide process-specific memory segments. For task switching and multitasking, to facilitate multitasking, the 286 included task state segment or the TSS. So it stored CPU state information for task switching, and the interrupt descriptor table or the IDT manage memory protection, exceptions, and hardware requests. And lastly, the task gate mechanism where it allowed switching between tasks, although it was inefficient and rarely used in practice. Of course, we have the challenges and limitation about this 8286. But despite its innovation, the 286 has significant drawbacks. So those drawbacks are first, backward compatibility issues. So older 8086 software was not compatible with protected mode. Once switched to protected mode, the CPU could not return to real mode without a reset. So to return back to the real mode, uh, they need to reset. Oops. Next is the performance penalties. The new privilege mechanism introduced overhead and reducing efficiency, and the 286 could only work with 4 simultaneously 64 KB segments, limiting practical multitasking benefits. So it's still limiting the practical multitasking benefits. So because of that, Bill Gates' criticism and the future of 86 multitasking was being stated. So due to this limitation, Bill Gates famously referred to the 286 as a brain-dead chip. Microsoft found it impractical for running multiple MS-DOS applications in a multitasking environment. However, these early challenges paved the way for improved protected mode implementations in later processors, leading to redefined multitasking capabilities of the Intel 8386 and beyond. So that's all for the part 3 of the evolution of CPU.